For CO2 capture from humid flue gases, pressure swing adsorption technology offers significant energy savings with respect to conventional amine absorption technologies. Two important candidate adsorbents are 13X zeolite and CAF20. 13X zeolite is a cation exchange fungicide zeolite with sodium extra framework cations. Per unit cell of 13X zeolite, we have 106 atoms of silicon, 86 atoms of aluminum, and 86 extra framework sodium cations, yielding a silicon to aluminum ratio of 1.23. The CO2 congregates around the extra framework cations, and such congregation effects result in thermodynamic non-idealities for separation of CO2 nitrogen mixtures. My talk today is on the influence of the presence of water on the CO2 capture characteristics. And I wish to compare the performance of 13X zeolite with CAF20, which stands for Calgary Framework 20. This metal organic framework has gained considerable attention in recent years after the publication by Shimizu and co-workers from the University of Calgary, University of Alberta, the Svante Corporation, and the DASF Corporation. See also the paper by Nguyen and Rajendran on the CO2 water adsorption characteristics. I have other presentations on CAF20, on 13X zeolite, segregation and congregation effects, and the failure of the IAST. All of these can be viewed on my YouTube channel. Let's start the discussions by first comparing CO2 nitrogen separations using these two adsorbent materials. Wilkins and Rajendran published experimental data for adsorption of mixtures of CO2 and nitrogen in 13X zeolite at a total pressure of 97 kilopascal and temperature of 296 Kelvin. The experimental data were obtained for varying amounts of CO2 in the bulk gas mixture. Here is a plot of the experimental data. The component loadings of CO2 are indicated by the red circles. The component loadings of nitrogen are indicated by the blue triangles. The IAST predictions for the component loadings based on unary isotherm data are indicated by the dashed lines. For CO2, the dashed lines are in good agreement with experimental data. However, for nitrogen, the component loadings as measured experimentally are significantly higher than those predicted on the basis of the IAST. The CO2 nitrogen adsorption selectivity is plotted here as a function of the mole fraction of CO2 in the bulk gas mixture. The IAST severely overpredicts the adsorption selectivity of CO2 with respect to nitrogen, and the experimental data are significantly lower. The continuous lines in the graphs here and here are the calculations based on the real adsorbed solution theory. In order to rationalize these results, we conducted configurational bias Monte Carlo simulations for CO2 nitrogen mixture adsorption under conditions similar but not precisely identical to those in the Wilkins-Rajendran experiments. These CBMC simulation data are available in the ACS Omega publication from 2020 that is cited here. The experimental data, the CBMC simulation data are presented here, and the CBMC data are compared with the calculations of the IAST. As is the case with the Wilkins-Rajendran data, the CBMC simulations also show that the IAST severely overpredicts the absorption selectivity of CO2 with respect to nitrogen, and we need to introduce activity coefficients in the RAST formulation to capture quantitatively the CBMC data on component loadings and selectivities. A precisely analogous situation holds for absorption of mixtures of CO2 and methane in NaX zeolite. The CBMC data show that the IAST overestimates the CO2 methane adsorption selectivity to a significant extent. On comparison of CO2 nitrogen with CO2 methane selectivities, we note that the overestimation of the IAST is higher for CO2 nitrogen mixtures than for CO2 methane mixtures. Now, so far what we have achieved is to show that the CBMC simulations are in qualitative, are in agreement, albeit not entirely quantitatively, with the Wilkins-Rajendran experiments. We need, however, to appreciate the reasons for the failure of the IAST as observed in the two sets of simulations here for CO2 nitrogen mixtures and for CO2 methane mixtures. We shall now demonstrate that the failure of the IAST is due to the inhomogeneous distribution of guest species within 13X zeolite. In particular, we wish to demonstrate that CO2 congregates around the extra framework sodium cations. In order to demonstrate this, we carried out CBMC simulation data to determine the spatial location of guest molecules within the host framework and the intermolecular distances. The radial distribution of guest pairs is plotted against the distance between the guest pairs. The red line is for the CO2-CO2 distances. The blue line is for distances between CO2 and the extra framework cations, and the black line is for distances between CO2 and nitrogen in a CO2 nitrogen mixture at a total pressure of 100 kilopascal, temperature of 300 degree Kelvin. The first peaks are indicative of the segregation or congregation effects for CO2 nitrogen mixtures. We note that the CO2 molecule is closer to the extra framework cation than it is to the nitrogen pair, nitrogen partner. Consequently, nitrogen suffers less severe competition with the CO2 molecule because it is further away from CO2 and CO2 is closer to itself or to the extra framework cation. The same is true for CO2 methane mixtures. The red line is for CO2 distances in the mixture. This CO2 is much closer than CO2 methane, and CO2 methane distance is larger than the distance between CO2 and the extra framework's sodium cation. In other words, methane suffers less severe competition due to congregation of CO2 around the sodium cation. In order to drive home this point, we also carried out simulations for CO2 nitrogen mixtures and CO2 methane mixtures in a Fauger site with a silicon to aluminum ratio of infinity. In other words, no aluminum atoms and no extra framework cations. In this scenario, we would expect no congregation of CO2 around the cations because there are no cations present. And we note that the intermolecular distances, CO2, nitrogen, and CO2, are all practically the same. An identical situation holds for CO2 methane mixture adsorption in all silica Fauger site. The distances between any of the pairs, CO2 pair or CO2 methane pair or methane pair, is practically the same. Introduction of extra framework cations leads to congregation of CO2 around those cations, and for both these mixtures, the partner molecules, nitrogen in this case and methane in this case, have to incur less severe competition with CO2 for mixture adsorption. And this explains the reason that the IAST that presumes or assumes a uniform distribution of adsorbates overestimates the adsorption selectivity. Let's turn our attention to the adsorption of mixtures of carbon dioxide and nitrogen in CAF 20. The experimental data of Nguyen and Rajendran, published in Chemical Engineering Journal in 2022, are shown here, and the experimental data for mixture adsorption shown by the red squares for CO2, black squares for nitrogen. The nitrogen scale is on the right axis, the CO2 scale is on the left y-axis, and the experiments were carried out at a total pressure of 97 kilopascals and a temperature of 295 degree Kelvin. The IAST estimates of CO2 loading and nitrogen loading are shown by the blue crosses. We note here that there is a slight deviation between the IAST estimations for nitrogen loadings as compared to the experimental values. Now, in order to understand these small deviations from ideality that were reported in the experiments by Nguyen and Rajendran, we carried out molecular simulations for adsorption of mixture of CO2 and nitrogen at a total pressure of 100 kilopascal at a temperature of 298 Kelvin. On the x-axis, we have the variation of mole fraction of CO2 in the bulk gas mixture. The red circles are the CO2 loadings from molecular simulations. The blue triangles are the nitrogen loadings in the adsorb phase, and the axis for the nitrogen loading is on the right-hand side. The dashed lines are the estimates of the IAST. What we observe is that the IAST is in excellent agreement with the CBMC simulations for mixture adsorption of CO2 and nitrogen. And therefore, these small deviations observed in the experiments of Nguyen and Rajendran are perhaps due to the fact that the experimental data that is reported and presented here are based on breakthrough experiments that are not conducted under precise isothermal conditions. In order to further verify that the IAST predictions for CO2 nitrogen adsorption are in good agreement with the data from molecular simulations, we carried out another set of molecular simulations in which the composition of the bulk gas mixture is maintained at 5% CO2, and the total fugacity of the bulk gas phase mixture is varied from 0 to 100 kilopascals. Again, we see that the IAST provides excellent estimates of both CO2 loadings and nitrogen loadings. The details of the molecular simulations are provided in my paper published in Separation and Purification Technology 2024. Let's look at CO2 capture from humid natural gas. I show here configurational bias Monte Carlo simulations of the unitary isotherms for water, blue triangles, CO2, red circles, and methane, green squares. The mixture adsorption of CO2 and methane in CAF 20 follows the predictions of the ideal adsorbed solution theory as demonstrated in the CBMC simulations for mixture adsorption of 50 mixtures of 5% CO2 and 95% methane. The CBMC data are shown by the red circles for CO2 and green squares for methane. The dashed lines are the IAST predictions using the dual site Langmuir-Freundlich fits of the unitary isotherm data for CO2 and methane. We see that the predictions of the IAST are excellent, and CO2 methane mixtures behave ideally within CAF 20. Let's turn our attention to mixtures of CO2 and water. Let us look at the data of Lin, Nguyen, Rajendran and Shimizu, published in the science paper. The experimental data are shown for CO2 water mixture adsorption at a total pressure of 97 kilopascals for varying degrees of relative humidity. The experimental data for CO2 loadings in CAF 20 are shown by the red circles, and the blue triangles are the component loadings for water. Now, additionally, I show the unary water loadings for the set of conditions in the experiments indicated by the blue line. The unary loadings for CO2 absorption is shown by the continuous red line. Also shown in this figure with the dashed lines are the IAST estimates. The calculations of the IAST are described in detail in a previous presentation on my YouTube channel, which serves as a tutorial on the use of the IAST. There is a lot going on in this slide, but I draw your attention to this remark made in the science paper, which states the distinct shift in the water isotherm in the presence of CO2 compared to the pure component isotherms confirmed the suppression of water sorption for CO2. Let's see what it means. Here is water sorption for mixture adsorption, shown by the blue triangles. For unary water, these are the loadings for water, shown by the continuous blue line. So the water loading in the mixture is significantly lower than the loading of the pure component, leading the authors of the science paper to postulate the phenomena of suppression of water due to the presence of CO2. Strictly speaking, however, we should not compare the unary loadings, but rather the IAST estimates of the loadings for water and CO2 with the corresponding loadings in the mixture. If we do that, we see that for humidities lower than about 45%, the water loadings for mixture adsorption lie below the IAST estimates of the water loadings, and therefore the phenomena of suppression of water is strictly valid below a relative humidity of 45%. For higher percentage humidities, we see that the water loadings are higher than the IAST estimates, and the suppression of water is not operative at higher values of relative humidity. Be that as it may, we can conclude that for relatively low values of percentage relative humidity, say less than 45%, there is suppression of water, and this is a persuasive advantage for use of CAF 20. I discussed all of this in my previous presentation, but it's instructive today to compare these results with the corresponding results for 13X zeolite. The graph here on the left-hand side presents the data on CO2 water competitive adsorption in 13X zeolite at conditions almost identical to those used for CAF 20. The data here is from Wilkins and Rajendran in the journal Adsorption, published in 2020. There are important differences between CO2 water competitive adsorption in 13X zeolite and those for CAF 20. Firstly, we note that the experimental data for water loadings indicated by blue triangles, the CO2 loadings are indicated by the red circles, are in reasonably good agreement with the IAST estimates. In a future presentation, I will explain to you how these IAST calculations were performed. But there are some important points to note. Firstly, that the unitary water loadings indicated by the continuous blue line and the IAST calculations for water loading practically overlap each other and agree with the experimental data, which suggests that the adsorption of water in 13X zeolite is significantly stronger than that of CO2, and CO2 loses the competition with water adsorption, and there is no hint of any suppression of water adsorption due to presence of CO2, as is the case for CAF 20. Remember from my remarks on the previous slide, I said for relative humidities less than about 45%, water adsorption is suppressed by the presence of CO2. I will explain that in a future presentation. There is no such suppression for 13X zeolite. Another point to note is that the water loading is of the order of 17 to 18 moles per kilogram compared to loadings of about 8 moles per kilogram for CAF 20. So a significant of water gets absorbed by 13X zeolite, and this is not a desirable feature. So from the point of view of CO2 water competitive adsorption, one would conclude that CAF 20 is to be preferred to 13X zeolite. There are a number of loose issues that need to be tied up, and that is the reasons for the failure of the IAST. All of these will be discussed in a presentation to be made a few months down the line. For now, I would like to conclude by saying that for CO2 capture from humid flue gases, it appears that CAF 20 has some significant advantages over 13X zeolite.